Mm. Yes, I need. We continue uh, to, I guess, cascade analysis. Um, Last week we learned about GASCA's calculus, but the one is based on concentration. So today we will learn about GASCA's calculus, but this it's time-based, time sliced GASCA's calculus. This is based on paper 5, optimization and targeting of supply demand of biogas system, gas escape analysis framework. So, good afternoon. Today
Good afternoon.
we focus exclusively on gas escape analysis, gas system escape analysis, GASCA. So up until now, pinch analysis was steady state, designed for factories running 24/7 with flat flow rate, meaning a similar constant flow rate. But what happened when we integrate renewable biogas into a municipal network? So meaning at 7 a.m., thousand of residents using their cooking stove, the demand surge, but at 1 a.m. morning, the cooking demand dropped to zero, but electrical base load remain active. So if our digester, we go through this paper, it's about the anaerobic digester. This is based on local case study happened in Johor. So if our digester produce a flat rate of gas, we have an immediate mismatch. So to size our storage tank and digester perfectly, we must transition from the concentration P, which is what we learned last week, to the time-based pinch analysis TBPE. So let's look at how we convert electrical and vehicle fuel requirement into equivalent raw energy unit counting for conversion losses. So the main message of GASCA is sizing decentralized municipal biogas network under dynamic hourly supply demand chain. The paper is available. This is how it like. So from raw feedstock, going to the anaerobic digester, then it lost to the biogas storage. From the biogas storage, we have upgrader. Then for the cooking oil, vehicle fuel, then cleaning, um, gas from the cleaning go to generating turbine boiler. This is for the heating application, electricity. So this is the application, the blue box. uh, the raw utility requirement cannot be added directly. Application Z and gas purity level K exhibit distinct energetic efficiency and purification process. Oh, stop. Mm, yeah. Oh, mm. Also, again, this is about this paper. Today is using gas cascade analysis, but it's time based instead of concentration pinch. So start again. The raw feedstock. I'm showing this. The raw feedstock goes to the anaerobic digester. So the gas that being produced by the digester goes into the biogas storage. From the biogas storage either being upgraded as cooking gas, vehicle fuel, it be clean, then use for the boiler and generator turbine. So the blue box here refer to the application the biogas. Then the biogas decentralized system is an important technology being developed country nowadays. As one of the energy efficient, eco-friendly technique for production of bio energy beside EVs or becoming petrol reduction of disposed waste volume of greenhouse gases. So for the overview of the GASCA started from here. Energy demand of the application set require the gas split level K. Uh, one is then conversion factor. So all of this um, unit, all of it's representing as in equation, not a function, to do time slice. This discrete analysis. Let's start with the energy equivalent of total raw gas demand. LT for each time plus T is calculated to a series of step as well. So because it's a time slice, it doesn't matter is it one day or 24 hours, or it's just for 10 hours or 6 hours. Yeah. So from that the value regardless of the hours that you know is the here minimum, let's say 6 hours. So for 6 hours, so we can find the pinch within the 6 hours data. But for this paper, it's based on 24 hours. So we have time slice around 24. Okay. So the first step of GASCA require the data collection, extraction of relevant data for analysis later on. So once all the raw data is completed, we can conduct to pay the uh, derivation of equivalent. Yes, derivation of the energy equivalent of raw gas demand for each application involving this equation. We start with equals. So energy equivalent of total raw gas demand LT for each time less things and its for a series step as follows. Start with FPKT, the energy equivalent of that biogas feedstock with different quality level K, fulfilling the energy demand of application is it at each time slice it's FPKT equals to summation of PKZT referred to energy demand of application is Z at each time slice T. So in this case, they're going to yeah. So D here refer to derivation of energy demand for each application from the raw data. Yeah. So this is the unit conversion. How about F applied this denominator is the conversion factor to account for the energy losses associated with different application. That one is able to apply F applied KZ for electricity is 35.9%. Yes. That one is for electricity because the demand, there are three demands. People, we have demand for NGV, natural gas vehicle, cooking gas, then electricity. So each have their own next is because the table is being like this. Oh yeah, like this. From the raw data, we do the calculation using equation equation one until L2, yeah, until three, yeah, three. So demand for each the cooking gas, the GV, electricity, you need, you need to calculate it. Yes. Okay. Let's go to the next. Uh, One of these TBPA design approaches include the supply chain okay, planning using pinch analysis for meeting the demand of a specific time frame with maximum profit. Wait, It was also applied in carbon emission, energy footprint network, So this is some of the application for TBPA, time-based pinch analysis. This is what we learned today is one of the applications. So for power system optimization, TBPA was applied for designing and optimizing an isolated energy system and the monetizing of hydrogen generator and state. So the essence of TBPA is to determine the targeted value based on the time-based energy data vehicle cascading approach, graphical approach. Uh, um, so for this paper, specific paper, research proposed TBPA known as GASCA, this case, to target the minimum biogas storage size, minimum biogas generation capacity for AD. AD referred to another big digester. Biogas charging and discharging profile of AD subject to a set of biogas demand profile for different biogas purity level. Oh, methodology. The cascade basis for biogas energy system. The first column is time. It doesn't necessarily 24 hours. Depend how much data given to you. Then energy equivalent of total raw gas demand LT. Okay. So the first methodology here is to prepare derivation of energy equivalent of raw biogas demand for each application before we can get LT, because LT is equal to FP. Yes, okay. One by one. Mm, next is after we calculate FP, then we need to calculate FP row. D is given. D here, because if you refer to derivation table 4, there's a value of D, D for each of the application. So where do we get the D? So D is given here in terms of this value. Yes. So you notice there is no demand at times that this is taking into account for 24 hours. So this is the hour one, meaning 1 a.m. Yeah, until what, 12 a.m. Yeah, throughout the day. Pukul 1, pukul 2. So the demand for NGV start at pukul 7 lah. Electricity throughout the day, it will not reduce. It will reduce, but it will not stop. But demand in the early morning is lower. Cooking gas similar, started at 5, oh, sorry, 4 p.m. Oh, sorry, 4 a.m. It, okay. Uh, so the first purpose, the first methodology is to prepare this table. So now you know where to get the D. FP is based on equation 1, 1 is 1. Where to get FP applied? The one is from table 2 is constant. Yeah, let's see, constant. Mm, yes, let's apply KZ. So you will have each of the application is different value. So you cannot use 35.9 because it's percentage. You need to uh, divide by 100. What is okay, FP row now. So to calculate FP row, so FP row is equal to FP, which is what you calculated previously, equation 1, and FP upgrade. So FP upgrade is well, uh, the energy variation due to evaluating process being accounted by conversion factor. So this value is from table 2 as well. Table 2 FP row. F F upgrade is this value, which is the upgraded biogas. So 95.2%. If it's using raw biogas, then you can use 100%. But since if all of the gas is either cleaning or what else? Nothing like cleaning or yeah, upgrade. So we don't use raw biogas. So we need, which is why you need to select this value and give a 20%. Don't forget to divide by 100%. Yes. Okay. So that's all for the FP and FP row. So next is to find the LT. LT. So LT is equal to um, summation of FP row. So FP row we have three: electricity, NGV, and cooking gas. So for this case of times less until 3, only one FP row available. So that's why the value is similar. Otherwise, you need to add it up. So FP row for, let's see here. Now the 4 times less 4. Bureau for electricity 3106 plus 2626. You get 4732.7. And you do the rest. So this method is much more, it's not steady state, it's a dynamic. Yeah, because you see here, there's no usage of cooking gas after, oh, the 6. Okay, because this is for household. Yes. Next, since we finished with this table 4, so this is not a pinch yet. The pinch start here. So this is the gas cascade analysis. The initial iteration. Wait, mm, okay. So the first column is for the time slice from 1 to 24. Total gas demand LT is what you have determined before in table 4. Yes. Then this GT is the gas generation. So in this case, it starts with 5,400 megajoule. We don't know yet the value, the actual value for GT, because GT is, so we need to later we see, we need to recalculate after each iteration. So in this paper, why it start at 5400? Okay. So I'm not sure how, but they choose 5400, 5400 as the first value of GT, and then you need to calculate NT, net gas energy. So to calculate, you see GT is arbitrarily adjusted and assumed to be constant in each times as this. So this value, once you choose or given to you in the patient letter already, let's say, so just use the value first, then you do the iteration, and it will change every time you do the second iteration, third iteration. So net gas energy NT is equal to the equation for this equation. So NT is equal to GT minus L. Yeah, NT is GT minus LT. Doesn't matter if it's negative. You can use negative, no problem, but you can also use what is it? A bracket to signify that it is a negative value. You see 5400 minus 9109 because it's negative. Okay, salah. Yeah. Okay, next is CT. CT. So to calculate CT is charging if the net gas demand empty. this value NT, is a positive value. So you calculate the CT based on equation 5. The charging discharging gas energy value are derived from the values in column 4 based on the sign indication. So, okay. So if the net gas demand NT is a positive value, the charging gas CT is calculated using equation 5. But if the net gas demand is negative, we need to calculate DT. Yeah. So the way we calculate is different. This one is NT multiplied with F charge. F charge, that one, the value is from table 2. Still. So in this case, F charge is 100%. 100% is easy. It's similar value. So CT is equal to NT, VT is equal to NT. Divide by 1. Yeah. You see? Similar value, regardless. But you need to know the way it calculates. Next is QT. So QT here is so to calculate QT, the equation is QT equal to QT minus 1 plus CT plus GT. So CT DT is available in the table. We calculate before in DT. But QT minus 1. So QT minus 1 in this case is 0. Because any cascade analysis, including water cascade, it will start with 0, including gas cascade analysis based on the time base. So 0, what's it? 0 plus CT, yeah, plus DT. So the value is the same. How about the second value? So the second value is 2766 plus CT, it becomes 6059. What happens if you found, if you mm, face this negative value? So mm, it will subtract the value from 11,000, 11 minus 2709. So it becomes 7364 and so on till the end, until time slash 24. Then Uh, oh, sorry. Until here. Okay. So that's it for the initial iteration GASCA. So next, this is the important part, the difference between water cascade analysis, the gas cascade analysis, which is both based on the time pinch. Okay. Next, so to determine either we need another iteration or not, so we calculate P. It should be noted that invisible cascading is first conducted assuming zero inventory, which is when you do the initial iteration, start with zero. To determine the most negative inventory, second cascading is then conducted. Is conducted with this value plus as the initial inventory, each time initial inventory to initial, final inventory to final determine. So the percentage change P in the initial and final inventory is calculated using equation 8. So P percent equal to Q final initial divided by Q initial. So this Q final, Q initial, it is based on this, based on this initial iteration. So in this case, Q initial is we start with zero, which is normal for uh, initial iteration. Then Q final. Yeah. So this is how you calculate. This one is G. Um, so to calculate those, you need to use these two values. So Q final, 18,491 minus initial divided by initial, which is zero. So zero. Yeah, can't see what to do. So, so since you need to guess another GT because this is only the first iteration and it the pinch is not there. When there's a pinch, one of the QT is zero. Then you know it's a pinch analysis. Okay. So next we need to identify a new value for GT using the first initial iteration. So GT equal to GT new equal to GT all, which is 5400 minus Q final minus Q initial divided by T. So T here refer to how many time slice or total period. In this case, it's 24. It depends if the uh, question give you only 6, so T only 6. So once we have a new T, we do another iteration. But before we go through the second iteration. So from the first, the initial iteration, with the biogas capacity 5,400 megajoule per hour, the capacity of biogas storage was determined to be 24,432 megajoule, whereas the initial and final energy content at biogas storage were determined to be 0 and 18,191 megajoule. So the finding indicated, so this finding is based on this data, initial 0, final 18,000, so maximum 24,000. That one is the capacity of the biogas storage. So since there are no zero gases, then uh, we don't use uh, gas. That's why there's no zero gases. So 18,191 must be dumped at the end of the daily operation, the Q final. This is to ensure the stability of the biogas storage system. Hence, in order to minimize the wastage of biogas resource via dumping, there would be a need to reduce the final energy content, the Q final, by reducing the size of the gas generation. So this is where the reason why we need to determine a new GT. From this analysis, this is based on the initial iterations. Two conclusions can be drawn. Firstly, if the final gas content is more than the initial amount, the Q initial, then the AD is oversized. On the other hand, if the final biogas content is less than the initial amount, then the AD is undersized. So meaning, once you do the time size, the value for initial and the final must be equal. So from the calculation, percentage estimated using question 7, but the first station was found to be less than 0.05%. If the percentage change was larger than 5%, the question would be repeated to determine the new size of biogas generation capacity GT new by using equation 8. The target of 0.5% was set as a tolerant to ensure accuracy of the result. It was also to ensure consistent daily energy profile of biogas storage by dumping the biogas before the next day without accumulating the biogas. Okay. So next is to find another GT, GT new. So using the value from the initial iteration. So we have this is the old value for GT 5400 minus 18491, the Q final minus 0 divided by 24. So we found out that the value for to find out the value, the new value for GT is 4629. Okay. Next, so we do the another uh, iteration. So this time using the new value for GT, repeating the same thing. So since the value LT is similar, LT is from table table apa? Table 3. It's from table 3. So gas generation GT is different now. Next is we need to recalculate NT and CT. Oh, sorry, we need to calculate NT. So to calculate NT, you use equation 4, GT minus LT over time 1 to time 24. Next is to calculate CT and DT. If the value of NT is positive, then NT is multiplied with F upgrade, sorry, F charge. If the value of NT is negative, you divide it with F discharge. So F charge, F discharge is available in table 2. Here, both is 100%, so it's easy. Divide by 1 or multiply by 1. And then determine QT is Ya kan? So it doesn't show the second iteration here. Yeah. The second iteration should use a new Q initial of it. What was the lowest number? 508 times less 2. That's worth. So this will be the new Q edition with different value of GT. So we calculate again, then find the P, make sure P is less than 0.5%, 0.05%. If it's bigger than that, which is, it must be bigger than that, since the Q initial here is at 737, not 508. Yes. Yeah. So how many? Cascading require is in the word. Mm, correct. Now the do iteration. Initial, then another one, and last one is it's 737. Mm, okay. Once the cascading analysis was completed, the optimal biogas generation capacity of AD was found to be 469 megajoule per hour, and optimal biogas capacity of 16,122. This is based on the final iteration. So the optimum biogas generation capacity is 4,629 megajoule per hour instead of 5,400. Then the optimal biogas capacity is 16,000. 16,000. Not 24,000 on the targeted initial final energy content of request to a part to be equal at 727 estimated in the receipt, the page point of the 8 times less work that out in the first initial iteration of the is 508. So for the initial, they say it's an infeasible cascading in which Q initial is zero. That one doesn't need, you don't have to calculate the P%. Then once we determine the smallest value, which is 508 from initial iteration, becoming the Q initial, then it become the first iteration for a feasible cascading. That one you need to calculate the P%. Uh, uh, and if the value of P% is more than 0.05%, you need to calculate the GT. Yeah. Oh, I put exercise. Yeah. So this is time slash until 10 only. Yes. So why not we try this once? Since this is LT been given already, so you don't have to calculate. Oh, the shade of it. So again, so this is an exercise for you. We do it in class. So since this is an LT, so you don't have to calculate uh, derivation energy equivalent because in the end you have this LT. So it's been given. So you start your calculation to determine the value of uh, LT, sorry, GT. GT is, how about you start with, um, berapa sih ya? Start with 500 GT. Yeah, then 500 GT. Then you start calculating for NT, berarti NT, 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 CT, DT, QT. So you do the first iteration based on this is the initial iteration based on the Q initial equals to 0. Let's drop it. Use Excel. One is easy. If you like to clean it, it's That's fine. Mm, okay. If we do this, reduce the workload and then available ingredient. Yeah, like this. So this one start from, yeah, infection, infection blue, let's input the glue. Hmm. Inhibition. So it's look like this. Basically, I say. So you have your time slice, the GT, and the LT, GT, we start at 100. So NT is GT minus LT, is GT minus LT. Then we find the invisible, which is GT equal to 0. And then we do the cascading. It is 100 minus 300 become 200, and so on. Then you find out that yes, this is the lowest value. So this lowest value become the new QT. This is for the feasible. Then you do again. So pinch happen here. So this one, you need to recalculate the based on the feasible QT here. You need to to find out the P value first. Yeah, P value.
So meaning the lowest deficit
The P
neg-
value is
negative
let's say
300.
this would be the in this case you find out which is 300 minus 300 divided by 300. Oh, what is 0%? Right. It's okay. So meaning since it's less than zero, which is 0%. So meaning yeah, no need to find another G, in this case. But if the P% is higher than the GT, sorry, higher than the 0.05%, then we need to recalculate GT, find the new GT, then start again. So, yeah, so thank you. Yeah, because we haven't signed in, you can sign in. So, that's it for GASCA. Okay. The quizzes is available in it. You know.
And doctor, can you upload the worksheet for the exercises
So for
now?
the past 4 weeks, you learn about water cascade analysis. The one we use UPM system is called AMOS. That's the case study to identify either we need to regenerate or not the water. Then you learn last week is a gas cascade analysis, especially for the nitrogen integration. Then we go in detail for the regeneration as well. There are two types of regeneration for the gases. This is different. So for the gases, the purity level is not, it will not be 0%. There will be some impurities. But for water, yes, you can get up to 0%, which is pure water. Then today you learn about this cascade analysis based on the time slice optimization. So, so you learn about the steady state system until the dynamic system. So today is a dynamic system. Thank you. The recording will be available not today, tomorrow.